think we should start now. People. Okay, so welcome to the second afternoon session of the conference. In this session, we will talk about Lorentzian structure of quantum gravity. We'll have three interesting talks. The first of them by Seth Asanti from the University of Jena.
Yes.
So, the floor is yours.
Okay, thank you, Antonio. Okay, so thank you everyone for being here. Also, first of all, I want to thank the organizers for inviting me to this very nice conference. I was surprised by the invitation. It was a nice surprise, and I'm happy to be here. And also, it's nice to see familiar faces, of course, and I'm happy to meet new faces as well. I would also like to thank my collaborators. I mean, I've listed some of them here from whom I've learned a lot of physics. And actually, this talk I'm going to read now is collaboration with two of them here. So thank you. And I chose to talk about causality violations in Lorentzian path integrals for discrete gravity. Rather than giving you a whole overview of Lorentzian quantum gravity, I chose this specific one. It's sort of an example, just so that I give you a feel of how this works. So bear with me. Okay, so I'll just start with motivation. So quantum gravitational path integrals has become very common. Many quantum gravity approaches are formulated on this. And you can actually see the difference, the different quantum gravity approaches as in the way they choose their, for example, the geometry they defined, and also the action associated to this kind of geometry. So, for example, in spin forms, you find that your geometric degrees of freedom are based on spins and intertwiners. In some other theories, it's based on some other things like lengths. So you can tell the difference between different quantum gravities from these path integral approaches. And because of that, you can actually ask fundamental questions like, for example, what are the fundamental degrees of freedom for quantum gravity? You can try to address kind of these questions. And here I try to address just one of them in this topic. So the theme of this whole presentation is about causality violations. So also we are focused on Lorentzian path integral. So in the computation of Lorentzian path integral, the main challenge you have to deal with is first how to compute the path integral. And it's a challenge because you have to deal with convergences and also high acceleratory integrals. And like we've heard in this talk, Bianca mentioned this yesterday, Euclidean path integral approaches have been one way, but they have limited use in this aspect. And Picard-Lifshitz method seems to be one way to kind of attack these high oscillatory integrals. And another question one can ask is, what are the configurations one should sum over in this path integral? And here we try to answer the question of whether we should allow some Lorentz topological changes, which are not really Lorentzian spacetimes. So I will argue at the end of the talk that the Picard-Lifshitz methods can also inform us about these questions. Maybe to make it a bit more precise, in 2 dimensions, it's been studied by already Raphael and Lyoko. For the causality violations arises in a form of that your action assumes some imaginary terms. And there are mainly two families of topological changing configurations. There is the Yamuk one and also the Traza one. The difference is that they come with different signs of the imaginary parts. So already there's a question which configurations are enhanced or suppressed because it depends on the sign of the imaginary parts, right? And Raphael and Lyoko already postulated that, okay, the Traza-like configurations are suppressed, and it was based on the sign. And also in 4D, we have done some work in effective spin forms, and we saw that actually if you enhance Yamuk configurations, these lead to very nonsensical results. So there's this question, which configuration should be enhanced, which configuration should be suppressed? And the question I want to ask is there a general formalism for these? So this is the theme of the talk. So I will start with a brief introduction of Lorentzian Reggie calculus. I'm going to do this with discrete gravity, and then I'll do the path integral in the second part of the talk. Okay, so let's just go with the first one. So if you don't know about discrete gravity, this is just a basic summary. So Reggie calculus is one formulation of discrete gravity. It's based on a discretization of the Einstein-Hilbert action. And the main features are that it's based on a simplicial triangulation of your manifold. So the main features you need to know or compute are basically these dihedral angles, deficit angles here, and they are somehow corresponds to the curvature as you want in the continuum. And these deficit angles are distributed on codimension 2 surfaces. And so Reggie initially formulated this in terms of length variables, but there are other possible variables you can do this. Okay, so that's a basic introduction of discrete gravity. And to talk about Lorentzian gravity, one has to, the main structures one have to deal with are Lorentzian angles as opposed to Euclidean angles. So I'll give you a flavor of what Lorentzian angles here. I mean, Euclidean angles, you think of them as angles between vectors. On a circle, you rotate a vector to another angle. Here, in Minkowski, you'll be on Minkowski space, so here is a 1 + 1 space-time. And now the angles are seen as boost. And you have to also, so here we have to specify angles between vectors even across different regions of the Minkowski space. And there's a summary of how to define these angles. So, for example, they are defined in this way. And the point here I want to make here is that you see the way we define these angles kind of depends on some choices between, like there are some imaginary terms here, and this depends on the angle. If there's a light ray between the vectors, then it picks up some factor of imaginary. And these are the imaginary terms that later show up in the action. So here, depending on the choice, there are two options. So I define them L+ and L- for the different choices, right? Okay, so you can lift this, so it looks like this was in 2 dimensions, but you can do this in higher dimensions. But I give here examples of 2 dimensions. So I call them hinge causalities, these imaginary terms that we saw. Also, I think Bianca already showed some pictures yesterday if you were around. So these are examples of some triangulations that appear in 2 dimensions. So here we call such a triangulation regular because you see that the bulk vectors here, they're exactly 2 light cones. Otherwise, then the triangulation would be called an irregular triangulation. So for example, there are more than 2 light cones, so you can see this as the trouser configuration. You go from the past and there are 2 futures you have to go. And also there is this Yamuk-like configuration. So in higher dimensions, there are more conditions one has to go through, like there is edge causality, vertex causality, and Renate and Jordan has already mentioned this. I mean, I think currently it's still an open question how to deal with these type of causalities. Okay, so with path integral in mind, we are going to be talking about path integral. So what we want to do here is to somehow define a complexified discrete gravity. And to do this, we'll consider a very simple kind of complexification, right? So here, I define this inner product term between 2 vectors, so A and B are just vectors in Rn. And so if I define it this way, so there's this exponential I-phi term, which you can think of as some weak rotation angle. Then, I mean, using this definition, you can think of it that in the Reggie picture, that I somehow complexify all my edge lengths in the same way. So there's just 1 degree of freedom, which characterizes this complexification, right? And so the main object that you will focus on is these complex angles. So I write it here. Maybe the details of this doesn't matter so much, but these angles, like in blue here, actually generalizes all the angles you can define in Reggie calculus. And already, as you see here, there are 2 ways I can somehow analytically continue these angles from either from 0 So yeah. So I should say that when phi equal to 0, you get Euclidean for sure. And if phi equal to pi or minus pi, there's Lorentzian with different signs. And so you see that the Euclidean angle and Lorentzian angle are already branch cuts of these kind of angles. So we can analytically continue these by following the procedure. And I just mentioned here that one can extend this by analytically continue this, and you find that you can continue this to angles from minus 2 pi to pi. And you see, like there's an example here, and you see that it's actually 4 pi periodic. Okay, so this somehow gives us a nice way to then define what the complex Regge action is, because you can use these angles to then define what the deficit angles are, and you actually find that the deficit angles are defined in this way, and then you can use that to define the Regge action. And the end result is that it's all well defined. So, so this is like the complex phi plane. Here you see, so if phi equal to 0, I pick up this imaginary, the Euclidean action, and phi equal to pi, I have these Lorentzian actions. But you see already the plus and minus signs show up here. So on this imaginary axis, there's already, what you find is there are branch cuts if my configurations are irregular, which means the light cone structures doesn't match. So that's why you see, so every time there's a branch cut, it will be on this line. But for regular configurations, these two terms are equal, so there's no ambiguity in defining what the Lorentzian Regge calculus is. So this is all nice. So yeah, so now I have this out of the way. I will try to use this to describe how to do the path integrals in this aspect, and also how the causality violations show up and how to treat them. Okay, so I'll do this via the Picard-Lifshitz method, as I mentioned at the beginning. Okay, so the idea of the Picard-Lifshitz is it's simple, and it's also very practical, actually. The idea is that, you have this path integral you want to compute. It's very highly oscillatory. That's what it makes it difficult. So the idea is that you want to somehow convert this highly oscillatory integrals into some sum of integrals which exponentially decays faster. So this is the idea. And there is a very formal steps that one can follow to define all these things. So I just summarized them here. So the first step is that, you complexify your domain of integration. So here I just call it X complex. And then you look for critical points of your exponent. Here it will be the action here. So these critical points will be in the complex domain. And then you use the critical points in the complex domain to find the Lifshitz symbols, which are the contours along which the integrand is decreasing, monotonically decreasing, and the imaginary part is constant. And then the last step is that then you want to express the original integration cycle into these symbols. So it's very clear how to do these things. And so we're going to apply this to deal with the causality violations that I mentioned before. And to do that, I'm going to use two very simple examples which also show up in quantum cosmology. So the first example is the no boundary proposal, which has showed up. You don't need to know any details of this for the purpose of this talk. The only thing you need to know is that in these cosmological spacetimes, the geometry of like the no boundary proposal look something like this. You have some Euclidean ball here, and then a Lorentzian de Sitter spacetime. And you can actually discretize this using these kind of triangulations. I will call them the ball model because they look like a ball. Okay, that's all you need to know. And the other example I will talk about is these de Sitter cosmology. So the idea is that there is okay, so I start from an initial cosmology for some scale factor I, and then I go to another scale factor final, and then so the one I call SH here, you can think of them as the lapse function. Okay, and so maybe one few little you need to know is that for this kind of models, there are some Euclidean saddle points, and there is a Lorentzian saddle point. And these type of models, I call them the shell model. Why? Because in the discretization, they look like shells. So there's a ball model and a shell model. And okay, so about the causality violations. These two examples actually manifest causality violations. So I show here, like on these, so this is the lapse axis. So if for some values for the height or the lapse, you see that your configurations are only Euclidean. So this is on this side, if the height is 0 and higher, you only admit Euclidean configurations. But on this side, there's a Lorentzian configuration, but in some region, you have some causality violations. So this is where it's irregular. So I denote this by some shaded. And there's a regular sector. Okay, so already in these examples, we see this interesting phenomena already showing. And so the question is, how do these irregular configurations, does it affect the computation of the path integral or not? Okay, so so in the first example, in the ball model, so yeah, I still have here the complex plane. And it turns out that you can compute the Lefschetz symbol, and the Lefschetz symbol is this green line. It lies on the phi equal to 2 pi axis, which means that it picks up this Euclidean action here. And I have blue here. We call them the anti-tymbals, which they act opposite like the tymbals. So there you have path. The paths are steep, ascending steeply. So right. So yeah. So actually, maybe this is a side result that you see that along these tymbals. So this is where you would actually deform your contour to. And we see that, yeah, this is along the phi equal to 2 pi, which actually leads to this choice of the action, the Euclidean action, which has been debated a lot in the literature, but it gives the same choice as Vilenkin and also Neil Turok and Job, who give a talk at the last end. So we actually confirm that maybe this is the correct choice to do. And the shell model is rather even more interesting. You have these interesting tymbals. So the green here is so this one is the tymbal. Yeah, so I mean, there are two saddle points, but let's focus on this one. I mean, this is not the actual tymbal. And there's a reason, because the anti-tymbal doesn't cross the original integration contour, so you only pick out this one. So maybe I did not explain before, but yeah, that's okay. But in this tymbal, you see that it goes across to this region and switches back to this region. And so in the computation of the path integral, we will have to deform the contour accordingly. So for example, in the ball model, if I want to deform this, so the original integration is along the Lorentzian axis, which is on this line. And there is a small irregular part here, which we saw before. So this is where the causality violations are. And you can try to compute the integral along this by deforming to this contour. And if you deform, so I show this in pink line, if you deform, so this is the deformed contour. So I'll do the integration here, and using Cauchy-Riemann, I can compute the integral along this direction using this. It turns out that this integration vanishes, so you basically have to do this integral, and it's easy. So the good thing is that you can also include the irregular regions, or you can try to find out without the irregular regions. But the point of this computation is that because you deform this part, it already picks up which side of the branch cut you should do your computation. And this picks out the side that suppresses these irregular configurations, or the causality violation configurations. So yes, so that's the main point. And also in the shell model, yes, so there is this original integration line, there are irregular configurations, but here you have to deform the contour along this path integral, and then you find that, so if I follow, so this integration will also vanish. Basically, I have to integrate along this line, but you see here there's an irregular region, so this is more interesting, but you have to, because there is a branch cut, you have to somehow follow the, analytically continue through the branch cut, and somehow picks you here. But the main point is that here, if we had to choose which branch, it would have been difficult, but the picalicious already gives us a way to do this. So if I follow the symbols, I see that, oh, for small values of the labs, which is, so, I mean, the way you should read these graphs are, so this is the phi angle at 0, the length gives you the radius, which is the labs here. So, so yeah, when the labs is small, I somehow have to deform in this region, and then for large, I have to switch to this side of the branch cut. So I am somehow on different sides of the branch cut. But the good result is that also, it always picks the suppressing side of the branch cuts for the irregular configurations, depending on the results. So that's the main message I wanted to tell you, which is that if you follow the picalicious procedure, it always picks you to the side where these irregular configurations are somehow suppressed. And so the main point is that you can therefore include these kind of configurations in the path integral, and you follow this method, it will not cause any problem. Okay, so that's the main message I wanted to tell you. So I'll just therefore conclude. So in doing this example, we've made a bit of progress computing the Lorentzian path integrals, and we saw that they are causality violating configurations, and they appear, they show up as branch cuts in your complex Reggie action. So this is in the discrete. And so, you know, using the Picard sheet somehow gives you a way to overcome these conformer factor problems, which I did not mention, but they show up if you do the Euclidean path integrals, right? So first of all, the Picard sheet gives us a good way. It gives fast convergence, and also the point is that if you follow the Picard sheet method, it allows you to include all the causality violating configurations, and you are fine. Okay. So as an outlook, so there are more examples one can test. So this was a very simple example. You can do this for higher dimensional integrals. Here we had only the labs function to integrate, but if the integration becomes complicated, it might, you know, be more challenging. But in principle, one can test these things. And also, I mentioned here application to effective spin forms. I think there's a paper on the archive this year, which you can check out. It somehow tries to answer these kind of questions. And I mean, one last point I made here is, for those who know about spin forms, there's the APRL spin form, that's the most famous one. Somehow these causality violations should show up because the kind of triangulations they consider are very much they very much show the causality violations, but there is no result if they show up or not. So with that, thank you.
Okay, so thank you, Seth. We have 10 minutes for questions.
I just have two comments. I mean, this method of using these Lefschetz symbols, I mean, it's okay. It's
Okay.
a valid method, but there is a simpler method which I used in my work. Maybe from 10 years ago. Okay. You simply put a measure instead of complexifying your reaction. You just put the measure. It's like you know, taking the real part of the complexified action to be a sort of a measure. But
okay.
And then by choosing a measure appropriately, you can make for example, the action to be finite. The path integral to be finite. So in that sense, there is a simpler method for getting the.
Okay, I see.
And the second comment, the thing that you were considering that essentially you are calculating the Hartle-Hawking, Lorentzian Hartle-Hawking wave function.
Right.
And but I think you should have chosen not the 4 simplest, but the 5 simplest, because it's 4 simplest is like in 2 dimensions you're just choosing a triangle instead of choosing a tetrahedron with a cut.
Right. Okay.
Do you understand? You know, you are 1 dimension lower than what would be natural geometric.
No, it's a 5 simplest actually. Okay, I was gonna. So
you see, this is a 5. This
it's
is a 4 simplest.
Oh, 4, you mean 5 in 6? 5 simplest is a 6 dimension.
No, you take 6 of those.
But I see what you mean. Actually,
it's a 5 simplex in 4 dimensions.
yes,
So
but
six vertices.
We use this already. We use actually 600 cell.
yes. So it's
We use it already. Actually, we use even a 600 cell.
yeah, I understand. But what maybe you should think of it as it's like a yes one. But this is just part of the simplex. Sorry, maybe it's a so you consider a 5 simplex. You put a vertex in the middle and then you connect. So
Yeah, you take 5 vertices and 6 vertices.
yes, right. So that's what we do.
One would be the 5 simplex, would be the
Yes,
boundary.
that's what we do exactly.
You did
This
that.
is what, and also we even do some more, which is you consider. So there are 3 types of homogeneous or irregular configurations one can do. So there's the 5 cell, which looks like the 5 simplex, and this is what we consider first. And there's a 16 cell, and there's a 600 cell, and you can do all these things. So you can do this and
No,
that.
but for me, the simplest one would be this with 6 vertices.
Yes, we did that too. So
Sorry,
that's fine.
I think we can discuss it because we have a discussion session after. Can we have a last question?
Okay.
Thank you, Seth. Really nice description of all of this. You explained really clearly the fact that these causality violating sectors are suppressed. Have you thought about a regime of the theory in which, okay, they're suppressed, but they're still there, so that we could answer the question of as to whether, you know, causality violating region could contribute to our amplitudes?
So I mean, I mean, in principle, they are there in the sense that you.
I understand you to be saying they're exponentially suppressed.
Right.
Is that right?
Yes.
Yeah. I'm wondering if there's some regime that we could look for them where that exponential suppression is as small as possible. I mean, sort of trying to look for them empirically.
I think that's, I don't know, maybe if one can.
Maybe you can think of it like
Yes,
during
sure.
the next talks and
Okay.
then the discussion. Maybe you have an
Yeah,
answer.
maybe let me think about this. Yeah. Thank you.
Okay, thank you again, Seth. Okay, so the second talk will be by Somati. So whenever you want.
Yeah, so I'm delighted to be here at this conference. Thanks to the organizers for giving me this invitation. So today I want to talk about the continuum approximation in quantum gravity, specifically, of course, in causal set theory, which is what I work in, but some way of calibrating it using some new methods in Lorentzian geometry. So here's the outline of my talk. I will begin by talking about the continuum approximation of quantum gravity in a slightly broader way that I think should be applicable both to discrete as well as continuum theories. So with or without discreteness, the idea of a continuum approximation and sort of in the spirit of what Baylock was talking about this morning. And then I'll focus on the causal set way of doing quantum gravity. And there we quantize the causal structure. All right, there you go. Okay. There you quantize the causal structure. And in this approach, we have a very specific definition of a continuum approximation, which comes about by random discretization. And of course, the question that is there that one needs to answer is whether the continuum emerges from your dynamics or not. And I will discuss some recent results as well as some slightly older ones, which suggest that there may be a chance for the continuum to emerge. But the question that one still doesn't have an answer to is whether the continuum approximation is really unique. So we know how to recognize it in some sense. how do we really call it a unique continuum approximation? And I claim that that's actually of relevance broadly to quantum gravity, all approaches, many approaches. And for this, I will then make a little advertisement about people working in these new ideas in Lorentzian geometry, where one is trying to calibrate closeness of Lorentzian spacetimes. And here in Nijmegen, you have Anne Radboud and her students, including Leo, who've been working on this. And I think these techniques are actually potentially very useful for quantum gravity. So let's ask the question, continuum approximation with or without discreteness. And so we have a scale in quantum gravity, which is the Planck scale. And the question is, of course, GR appears at scales much, much larger than Planck scale. And then you have Planck scale physics. Possibly, if you've got a continuum theory, you've got trans-Planckian physics as well, but I won't concern myself with that here. So we want GR to emerge from Planck scale. And so at some level, you have to ask, what Planck scale physics does GR have to forget? I mean, there's sort of a forgetting thing that you have to do. You can't think about all the details that are happening. There's some forgetfulness when you recover the continuum. And so if you think, if I call this, generalized quantum gravity degrees of freedom, QG, either it's discrete or continuum, I have to ask the question, at some scale, which is larger, significantly larger than the Planck scale, I expect that I recover my continuum geometry. So how do we recognize the continuum approximation when we see it? That's the kind of broad question that one would like to answer. So just very specifically, I mean, again broadly, but with a little bit more detail, if you think of this quantum gravity degree of freedom either as some kind of a quantum continuum space-time, quantum geometry which is continuum-like, or discrete in any one of your favorite approaches, then what are the distinguishing features that it has, first of all, at Planck scale that tells you what that detailed structure is? But say that you've got your dynamics and your theory spits out, say, a coherent state or what have you, some collective degree of freedom, which looks like space-time, then, if you have, for example, in continuum geometry, which is of lower regularity than what you expect of your classical theory, or you have some pre-geometric structure, we can have things that are piecewise continuous spaces, orbifolds, higher dimensional spaces. But at some coarse-grained scale, you expect that this should approximate space-time of the regularity that you desire. Okay? But at a scale, and this is kind of an important point here. And a question that you can ask in general is this unique? Is the approximation unique? If this quantum geometry approximates some space-time at this scale v, but it also approximates another space-time at the same scale v, then is there some sense in which these two spaces are approximately like each other at that scale? Okay? And I claim that this is actually of general interest. I mean, in causal set theory, we actually worry about this question quite a lot. And of course, you can ask, well, what does it mean for two spacetimes to be close at a given scale? And like I said, there's been some very interesting work of late trying to compare spacetimes, trying to understand when two spacetimes are close, and there have been recent techniques that people have been using. So let me get to the next part of my talk, which is going to be just on causal set theory. And this is a very brief summary. I apologize. I don't have enough time to do a full-blown introduction to it. So here you basically, to summarize, you quantize the causal structure. And we have these theorems due to these various people here, which tell us that if you have a space-time that is Lorentzian, so it's causal and it's distinguishing, then you can think of it as being made up of the causal structure pose set plus the volume element. And this is sort of the motivating set of theorems, motivating part of Lorentzian geometry for causal set theory. And when I say this is a poset, it's got this property of being acyclic as well as being transitive. And this leads to the causal set hypothesis, where you take this poset structure and you basically quantize it in a sort of first quantized way. And you do that by imposing an additional constraint, which is that of local finiteness. So I'm going to do my experimental demonstration of local finiteness by saying between these two events, the space-time elements that are to the future of this and to the past of this one, there's only a finite number of fundamental space-time atoms. And that's the definition of a causal set, a locally finite poset, and this is supposed to be the fine-grained structure of space-time. And so that's sort of the Alexandrov interval with a finite number of space-time atoms. And so in this hypothesis, we also have very crucially what we mean by continuum approximation, because we're motivated by this theorem here. And so order corresponds to the causal order, and the number corresponds to the space-time volume. And so counting replaces volume. Okay. The continuum approximation cannot be done via regular lattices. If you do a regular latticization, then the number to volume correspondence is not diffew invariant. So you won't get back what you want in the continuum approximation, so you have to adopt a random discretization via a Poisson process. The important thing here is that this discretization sets a scale. So you say that I recover the continuum as an approximation of this underlying ensemble of causal sets, but at a given scale, at that scale. And if I increase that scale, I would get a different ensemble of causal sets, because I would capture more of the fine structure of a continuum, and so on and so forth. So this is something to remember. There are various properties which I will not dwell on about the continuum approximation. One very important thing is that it comes with a rather annoying non-locality, which means that nearest neighbors are, you basically have a graph that's potentially of infinite valency. But the advantage that you have in doing this is that you have a discretization which preserves local Lorentz invariance. Okay, so how do we calibrate the continuum approximation? So is this approximation unique? So I've told you how to get from a space-time to the underlying ensemble of causal sets via this Poisson process. But can I say that it's unique? And this is actually a fundamental conjecture, what we call the fundamental conjecture of causal set theory. And we don't yet have a proof of this. But the idea is that if a causal set embeds into two different spacetimes faithfully, then those two spacetimes are close up to that scale. What we can do, on the other hand, so even though we don't have a proof of this, is to look at order invariance. That's things that don't depend on labels, which have some geometric interpretation, and use those order invariance to get a weak form of the fundamental conjecture, which we can prove depending on that particular choice of observable. And so we say that, and I'll illustrate this in a little bit. The question is, of course, which order invariants correspond to geometric observables? We have an entire list of these that we've constructed from discreteness, just from order relations. The latest being constructing a simplest thing like null GD6 in 2 dimensions. But let me take the example of a dimension estimator. So what do I mean by uniqueness here with respect to the dimension is that let's say that I have a causal set, or basically an ensemble of causal set, or a random causal set that I obtain from Minkowski spacetime in d dimensions. Then I can estimate the dimension. This is the Myrheim-Meyer dimension estimator by just counting the number of relations. This is a finite causal set. Count the number of relations in that causal set, and that gives me some function of the dimension which I can deconvolve to find out what the dimension is. Now, to get what the dimension is. Now, if the causal set also embeds into another space-time, then I can say, therefore, that that space-time must be like the original Minkowski space-time that I had at the scale rho with respect to the dimension observable d. So for example, if M prime is, has got an extra S1 sitting in it, as long as that S1 is not detected by my sampling of the space-time, so my discreteness scale is larger than the size of the S1, I will not detect it, and so I can say that this Mg is approximately like the Minkowski space-time. So in other words, what one wants to say is that if C has my dimension d, then it cannot approximate a space-time of dimension d prime not equal to d, okay, at this scale. So in other words, we have uniqueness, but associated with a particular geometric invariant. Now the question is, of course, is the continuum emergent from dynamics? And that's, of course, an important question. We have to deal with a very difficult problem. Because we have a definition of a continuum approximation, we do know what causal set is not like a continuum. And that's really important, because the set of causal sets that dominates the path integral, this path integral, which is over the set of all n-element causal sets, are these very ugly looking, they may look very regular to many people, but for us they look very ugly because they do look nothing like space-time. And these are layered causal sets. And you can, when you look at the contribution from these are overwhelmingly dominant. And you have to ask the question, well, these very highly dominant non-continuum-like space causal sets, what are they going to do to your path integral? Are they going to dominate? And so on. The important thing is that layered posets are not manifold-like. The ones that are manifold-like are very, very small in the space of all posets. And so the question you really want to ask is, do manifold-like causal sets stand a chance? And what they're up against is against the action that we have, the discrete action, which is a discretization of the Einstein-Hilbert action using just the order-theoretic structure that we have. And this is the Benincasa-Dowker-Glaser action, which is made up by counting the number of intervals of different sizes. And so I won't go into this too much, but this is basically what we have in the path integral. And the question, do manifold-like causal sets stand a chance? The answer, I think, is yes. They stand a chance because recently we've managed to show that. And this is a sort of series of work starting with paper by Loomis and Carlip, where they looked at the contribution from the subdominant causal sets, which are these bilayer posets. And using a very nice counting argument, they were able to show that the partition function from this subclass reduces to a simplified form, which can then be evaluated. And so you have a parameter range in which these things are suppressed. And likewise, we then went through and generalized this to show that basically, I think we can now show that all of these are suppressed. So the most dominant guys are not going to be challenging. 10 more minutes? Oh, great, okay. So do manifold-like causal sets emerge is, of course, a question, and that's something we don't yet have an answer to. We may have some little hints, but that's still something we don't know how to answer. So we still don't have an answer in the full path integral to the question, does the continuum emerge? On the other hand, there are these state sum models that we've been studying for a while, and they basically introduce a parameter beta, which we then analytically continue, so that what you end up with is a state sum model. These are Lorentzian state sum models, and these we've been studying for a while, and starting with two-dimensional intervals, generalized to these high dimensional, to the non-trivial topology of S1 cross R, as well as to 3 dimensions. And in these cases, what you find is that there is, in fact, what we can identify, and again, I want to use the term identify, as a continuum-like phase, and something that's not a continuum-like phase, okay? And the continuum-like phase is this random one here, this random one here. In the 2D case, you have these 2 phases, which in this phase diagram with beta as well as a non-locality parameter. And so these have been studied quite a bit. And the way in which we identify the continuum, so how do we identify, how do we calibrate that this is a continuum phase, is we track observables. We look at how observables behave. And for us, observables are very simple objects. They're basically order invariants. And as long as that order invariant has a geometric representation, we can then identify and say that this order invariant corresponds to this particular continuum geometry. And so we've used dimension estimators, the abundance of intervals, which is again like a dimension estimator, but in itself is also very specific to the continuum. We can use the action itself as well as the height. And basically, you can see that there are properties of these which look like the continuum. So you can read off in the sense of, with respect to this particular invariant, yes, it matches the continuum. And of course, these are very computationally expensive, as Bianca will attest to, because I think a lot of these final calculations were done on with a postdoc there in PI. So now, of course, the question is the continuum unique? So one has identified, okay, you found something and said, okay, it looks like Minkowski spacetime, but what have you found? I mean, is it unique? Maybe it also looks like something else. I mean, and how do you know whether those 2 spacetimes look like each other or not? And so I want to just, in the last few minutes, talk about how I might begin to calibrate the continuum approximation. And so this is, at some level, advertising work that people here have been doing, but also to say that there are some subtle things that we need as quantum gravity, quantum gravitors. And I just want to highlight that. And so the question that you really want to ask is, what does it mean when there are 2 spacetimes which are close to each other up to a certain scale? Because whatever your theory of quantum gravity, and I hope I've convinced you, or I'm trying to convince you that that's of relevance to any approach to quantum gravity, that at some scale you should be able to say that, okay, your fundamental quantum geometry approximates the continuum, but then how do you know that that continuum that you've got is unique? If it approximates it to another continuum, are those 2 continuum spacetimes equivalent up to the scales that you're looking at it, up to those physical scales? And the idea that Lorentzian spacetimes can be close via a generalized Gromov-Hausdorff convergence was studied by these people, and then more later by other groups, including the one by Annegret here. And the question that we want to ask is, can we define closeness with respect to a particular density? And then questions of convergence, etc. So one method is to use a uniform random sampling, and you can see that if I did that, then on these 2 spheres here, one with a little extension, then depending on the density of sprinkling, I could, with respect to that measure that I get, these 2 spaces would be considered to be close because I don't pick up any volume. Okay? And similarly, if I had these 2 balloons, one with this extra little wiggle from the string, these spaces are close to each other to the scales at which the string volume is small. Okay? So that's the kind of thing that I think is of general relevance to quantum gravity. And let me just, so I'll try to then skip this. So just to say that one of the things that one encounters, because you really want to ask the question, when are 2 Lorentzian spaces close. Even asking the question of Riemannian spaces and actually getting an answer, getting a metric on that space is difficult. But in the case of Lorentzian geometry, we don't even have a proper distance function on Lorentzian geometry. So getting and finding and defining a distance function is an important thing to do. And this is where there's been this very nice work on defining null distance functions on spaces which have time functions. And here we basically, the idea, so it was an idea due to Sormani and Vega, and there's been some really nice work on it subsequently, to use this idea for Gromov-Hausdorff convergence. But the idea is that you start with a piecewise causal curve, and you allow it to go backward and forward in time, where time, you have a time function, which is monotonic. So any space which allows a time function allows you to define these distances. And that distance is defined by the number of bounces, but at every time you bounce, you have to look at the difference in T2 minus T1, etc. So this is how you count, this is how you define the length. And this is why you get the distance function by basically taking infimum. So this distance function is a genuine distance function. And this is what they've done to study convergence of various spacetimes, etc. And there's a very nice workshop I attended where there's a lot of people working on this, and I think that these are questions that are definitely of interest to quantum gravity. So what I did with a student, well, this is still work in progress, but basically try to use the idea of null distance functions for causal sets by now taking the simplest class we know, which are these things we call 2D orders. And instead of looking at convergence properties, we're more or less looking at ways in which we can define a null distance function by looking at various embeddings into a larger lattice. And we've been playing around with this system, and we have some very preliminary results, which I wanted to just put up here, which tell you, what the distance between, say, a completely unrelated set of points and a completely totally related set of points is, and how that grows with number n. And so we're hoping that that the system we can study using these new techniques. When we come to things that look more like space-time, more like random orders, things are getting computationally very hard to do analytically, and so the hope is to try to put this on the computer. So let me just conclude by saying that the continuum approximation could be relevant to many approaches to quantum gravity, where at the scales of relevance, whether it's a mesoscale or whichever scale you want your quantum geometry to look like a continuum space-time. And there's always going to be this question of uniqueness, that if that quantum gravity, that geometry resembles one space-time and another, are those two geometries close, or are they just completely different? And I think so in CST, in causal set theory, the continuum approximation is recognized using geometric order invariance, but uniqueness is still not guaranteed. We just sort of do things that we can do, but really, ideally, we should have something like uniqueness. And I believe there are these new Lorentzian geometric tools that calibrate how close Lorentzian quantum gravity is to smooth space-time. But I think the question that I'm not sure people are looking at necessarily is that we really need the scale. We need to know at some physically relevant scale, are these space-times close? And that's the kind of questions that I posed to Leo here. Okay, thank you.
Thank you, Shamati. There are some questions. Where is the mic?
Question here.
Oh, yeah, but he has to give the mic. Yes.
Just because I didn't understand, or maybe you said it. The meaning of scale is something vague on purpose, or does it have a definition? When you say if at this scale these other two manifolds are a good approximation of my discrete thing, do you have a concrete definition of what scale
Right. So I think that the dynamics should give you that scale eventually. But I think so. So let's imagine a scenario where you have you have some mesoscale. So you have the fundamental scale at Planck scale, whatever your geometry looks nothing like the continuum, but you want at scales that are large enough, and that large enough scale is up to you to decide, you know, at what the physics should decide for you what that scale is.
But is that independent of the question of if they are close or not? Because if you use your definition of the scale to tell you how to say closeness.
So I would say, for example, and that's why this example of the Kaluza-Klein example, where you have an extra S1, if the S1 is very close and I want things to look like Minkowski, we think of Kaluza-Klein pretty much like that. We think that we're approximately in Minkowski space-time, but that Kaluza-Klein direction is so small it doesn't matter. So obviously we're looking at a scale that is much larger than the size of that circle. So in that sense, you need the scale to determine. Otherwise, these are two distinct spacetimes. So when you could ask, well, when are two spacetimes actually convergent as the scale goes to 0? And that's something that people study. But I think from the point of view of quantum gravity, what's more relevant is the question of these approximations up to a scale. And yes, the physics, at what physics do you want the continuum to emerge? These are things that have to go in. And I don't yet know a theory which tells you what mesoscale at which this should, but presumably at scales at which known physics begins to matter. I mean, right, yeah. So,
thank you.
Yeah.
Please, quick question.
Okay, the quick one is, if you go back to you had this very simple qualifier for telling two things are similar in a sense of a dimensional estimator. And I didn't catch where there I should see the discreteness scale. So yes,
this one?
exactly.
Yeah.
So where's the scale here?
This discreteness scale comes in the causal set itself. So I can't get a causal set ensemble is obtained from Minkowski spacetime at a given density, and that goes into so when I do the random sampling, right, I use a Poisson sprinkling to extract an ensemble of causal sets, that comes with a scale. So if I maybe just go back to
I get that. But
so this is a scale that goes in, and so you can keep that as your fundamental Planck scale, or you could keep it at some mesoscale.
Yeah. But in the end, I thought you were trying to say that if the dimensional estimator agrees, if the dimensional estimator doesn't agree, then the two spacetimes cannot.
Yeah, then it cannot I should say at rho. I'm sorry.
But how do I see the at rho in the estimator?
The at rho is here, and the estimator it comes into n.
Okay.
The number of elements that I have.
That
because it's
to
in a
rho
given. Yes.
Okay.
Yeah.
Thanks.
Okay, so thank you, Samatia, again for the next slide. Okay, so we have the last talk of this afternoon session.
Thank you.
Yes, by Job. So whenever you want.
I would like to thank the organizers to invite me. It has been a pleasure to be at this conference. Sadly, I won't be able to stay the whole conference, but still nice to see you all and re-interact with many people. So I will be talking about patent rules and existence of patent rules. I've decided to only show you some of the highlights because I would rather have you understand the key points and why it excites me and my collaborators, rather than show you all the details and show you all the nuances. So please keep that in mind. I will try to take you along the story and show you why I find this exciting. So this is work I've been doing with Neil Turok and more recently with Wei-Li Pen and in Dylan Zhou. Wei-Li is half in Toronto, half in Taipei, and Dylan is mostly in Toronto. So path integrals are maybe the most elegant way of understanding physics today. So for example, here you have the path integral for the standard model, and it's a beautiful theory and describes many, many different features of our universe with a single equation, which is kind of miraculous and of course due to Feynman. But the question is, do we really understand what this means? Do we really understand what a path integral is? And that's something I will be talking about. So of course you can do it for the standard model. Yeah, so I will be talking about that at length. Exactly. So another place where this arises is, of course, in quantum gravity. So Wheeler already said, well, the classical space-time should emerge due to interference of basically a path integral over superspace. So you can either write the Wheeler-DeWitt equations, or you can write the path integral, which is due to Claudio Bunster, who did beautiful work on that. And the idea is, how do you get classical space-time out of quantum foam or quantum fluctuations, and how to understand this path integral. And here I did write down a measure, but it actually is not a measure in this current form. So what are the problems? So if you read Feynman and Hibbs, the biggest book on path integrals, I would say, the original books, then you already see that Feynman had some unease about his definition. So he basically says, well, we have a path integral, and we will be talking about that at length, but it might not be completely mathematical rigorous. And he basically says, well, even though we might not have the mathematical rigor at the moment, hopefully in the future we'll be able to do better and find a mathematically rigorous definition of the path integral. And that's basically our motivation in the current project. The reason that we care is well summarized by a quote of Terence Tao, who's a very famous mathematician who you might have heard about, maybe even interacted with him. And he basically says, well, the point of mathematical rigor is not to make everything dull. It's not to destroy all the intuition. It's to distill the good intuitions and give us the most, basically, framework and the most powerful methods to tackle complex mathematical problems. And I would say that also applies to physics. So what's the problem? The first thing you should realize is that the path integral, if it is an integral, is only conditionally convergent. And you already know this can be problematic in sums. So what does it mean for something to be conditionally convergent? It means that even though the integral or the sum might exist, the sum of the absolute value is infinite. And of course, for the path integral, that's very easily seen, because if you have an action which is real and you take the absolute value of the integrand, then you see that it's 1. And integrating over the space of all paths is definitely infinite. And this is problematic because of many reasons, but the most easy way to see it is that for these sums, the order of summations becomes important. So if you normally calculate your average grade, you just add up all your grades and you divide by the number of grades. It doesn't really matter whether you first added math and then English, or did in a different order. But here you already see that if you take this alternating sum and you reorder it a bit, you get either the logarithm of 2 or half of the logarithm of 2. So it's really important how you order the sum. And this is also for path integrals, or I should say for conditionally convergent integrals, the case. So the most important or most well-known conditionally convergent integral is the Fresnel integral. So you see here that you have this integral over e to the power I x squared. And it's of course very famous because it's very close to a Gaussian integral, and you can define it in this limit. And then you find that it's 1 plus I times the square root of pi over 2. However, if you go to higher dimensions, it's not so easy. So for example, if you take an n-dimensional version, which I write here, then you can either say, well, I use square regularizations, and I use basically squares or cubes, and let the limit go to infinity, and then indeed you get this result to the power n. But if you say, well, why not use radial coordinates, then you find this result. And this result doesn't actually converge. So for n is 2, you find that it oscillates around what you would say the correct result. For n is larger than 2, it actually diverges. So this is just the same thing we saw before. If you change the ordering of summation, if you change your regulator, you can get a completely different answer. So that's one problem which potentially arises for these path integrals. The other problem is that the measure is actually not a measure. So in mathematics, we define integrals using measure theory. So a little bit of measure theory is, well, if you want to define a measure, you need to have a sigma algebra. So what is a sigma algebra? Well, you have a set over which you would like to integrate, and then you have a collection of subsets. So it's a little bit like a topology. And if in order for this set to be a sigma algebra, it has to satisfy these properties. So you have to have the whole set, it needs to be in the algebra. And if you have an element, then you need the complement to be in the algebra. So far, so good. But you also have that if you have a set of subsets, then the union, the infinite union, has to be also in the algebra. And if this is not satisfied, then you don't have a sigma algebra and you are in trouble. Suppose you have such a sigma algebra, you can now define a sigma measure. And the sigma measure is the building block with which you define your integrals. So what you need for this measure, which is basically a way to size up these subsets, needs that the empty set needs to be 0. Well, so far so good. You integrate over nothing and you get 0. But in addition, you have this property, which is the problematic one. So if you have an infinite set of pairwise disjoint elements in your algebra, so just blobs which don't overlap, then you want that the measure of this union, which is in the algebra by this condition, is equal to the sum, the infinite sum, over the individual blobs, which is also very natural. I mean, if I have 2 buckets of water, then the sum of the buckets of water is equal to, well, the putting all the water in one bucket and measuring it. And this is the problematic condition. So you need these infinite conditions, because if you want to define integrals, and I'm really sketching it here, is what you often do is you make sorts of test functions, like a step function basically, and you define the integral using this finite sum, and then you need to take some limits, and you take a supremum in order to be able to integrate over an arbitrary function. So you basically dominate your function, or you suppress, you find a set of functions which is below a certain function which you want to integrate, and then you take this limit. And that's normally how you define integrals. So what's the problem? If you take a Lebesgue measure, then that's just what you would normally do. You take a square or you take a cube, and you just multiply the sides together and you get your measure. And that works, and that is actually a sigma measure if you have a finite number of directions. So for a finite number of directions, the Lebesgue measure satisfies all these properties. Or if you take the infinite product of these measures, you run into a problem. And this is actually very well known in mathematics, and I think many physicists are secretly aware of it. But the problem is that if you have an infinite dimensional measure and it's translational invariant, and this is manifestly translational invariant, then the measure is either 0 or it's infinite. And the way to see it is that you can take, for example, a cube, and you subdivide it in smaller cubes, and then you want to be able to say, well, I take the sum of all these cubes, and I want to take that to be equal to the whole cube. And basically, you see that 1 is equal to 2 to the power n, this smaller cube. And if you take the limit of n to infinity, in order for this thing to have hold, mu has to be going to 0, because 2 to the power n is growing. And this is a big problem, because if you don't have a measure, you don't have an integral, and you don't have a path integral. Of course, there do exist infinite dimensional measures. For example, the Brownian measure, or the Brownian bridge measure, is a very good example, which is a measure which you can define abstractly, use the Bochner-Mindels theorem, but you can also say, well, I define it in this kind of way, so it's basically the free theory. Note there is no I in here, so it's Euclidean theory, so to say. And this is very powerful, and it doesn't satisfy the translational invariance. In that way, you can define this measure, and all mathematicians are happy. However, this is Euclidean, and this is, of course, the ingredient for the Feynman-Katz formula. But we would like to do real-time path integrals, and we would like to do it the Lorentzian way. So that's where we basically start. So just as Seth described, I will be using Picard-Lipschitz theory. And since he already described a lot of Picard-Lipschitz theory, I will just touch a few points. So the idea is you start with this integral, which is highly oscillatory. And here it's a one-dimensional integral, but it also applies to higher dimensional integrals. What you do is you say, well, let me take the integrands, analytically continue that into complex planes. So I will assume analyticity of f. Write out the real part, the imaginary part. And what you can see with Picard-Lipschitz theory, with a little bit of topology, that this integral is equal to this sum, where here you see ni determines whether the saddle point is relevant. So I should say you calculate the saddle point of f you calculate the steepest descent and steepest ascent manifolds. And now you first determine which saddle points are relevant to your integral, meaning which contribute to this sum. And you find that you get a constant term here, basically measuring the imaginary part at the saddle point. And you get this integral, which is absolutely convergent, because H will be the steepest descent manifold of J. So by construction, it's like a bell shape. So every integral, which is like here, basically integrates like this. It's absolutely convergent. It doesn't have any problems. So this Picard-Lifshitz business allows you to take a conditionally convergent integral and write it as a sum of absolutely convergent integrals. And that's a property I will use. So if you actually use this technique, and we applied this first to the no-boundary proposal, because there you can do all the integrals exactly, but we would like to go beyond, of course. If you now apply the same logic to this infinite dimensional integral, then the first thing what we do is we say, well, let's start with an n-dimensional integral, which is highly oscillatory. I missed an I see. If I now add a regulator, and I will let this regulator to be smooth, I want in the limit of R to infinity G to be 1, and I will assume that there are no poles, and it's basically a well-behaved regulator, and it can be a Gaussian or something resembling that. What you now can do is you can say, well, this integral is absolutely convergent, because the G ensures that it's absolutely convergent for R not being infinite. What you now can do is you can do Picard-Lifshitz theory on this n-dimensional integral, and you obtain this integral, where you integrate along these Lifshitz symbols, along the relevant saddle points, and you integrate along these steepest descent manifolds, and everything works out. But now, using the dominated convergence theorem, you can basically interchange the limits in the integrals, because it's an absolutely convergent integral. And what you find is that the G disappears. So you can define these oscillatory integrals using analyticity by integrating along the Lifshitz symbols, the steepest descent manifolds of a set of relevant saddle points, into this high-dimensional complex space, which is J. And if you now apply this to the continuum case, then you have to do a little bit more work, because some of the things don't really generalize to the infinite dimensional case. But what we basically say is you can define this path integral in terms of this phase factor, which is the phase factor at the saddle point, and phase factor which corresponds to the Maslov phase in WKB. And most importantly, you get this measure. And this measure we define using the Wiener measure. So along these symbols, the integrand starts to behave like a free particle in Euclidean signature, or better to say, you can dominate it by such a free theory. And since it's dominated by this free theory, it inherits all the properties, the mathematical properties of the Wiener measure. And for that reason, you can actually define these path integrals in this way. So just to speed up. So let's say that you have this definition and you can actually work with it. How does it actually look in action? So in order to see this, I will have to have a toy model, and I will just remain in quantum mechanics. And a very tempting toy model is either the harmonic oscillator or inverted harmonic oscillator. But these are too simple, because if you do the path integral, then you see, oh, there's only one saddle point, and it's the trivial saddle point, so it's not generic enough. However, there's this beautiful model, which is the Teller potential. And the Teller potential goes like this. So it's a constant defined by the cosh of x squared. So it's just a bump. And this is a very beautiful potential, because everything can be known. It's fully solvable. In particular, the propagator can be written in this way, where you sum over the energy eigenstates defined here. And the energy eigenstates are known in terms of Legendre polynomials. So you can calculate the propagator using these energy eigenstates completely, without any assumptions, without any approximations. And what we will be doing is trying to see how we can approximate, using this Picard-Lifshitz theory on the path integral, the same results, and see how it matches. So the first thing which you realize is that these path integrals, this propagator written like this, has been known in the literature for a long time, but there were kind of typos in the literature, and nobody actually took the time to evaluate these integrals. And what we find if we evaluate the integral is that you get these kind of interference patterns, and you in particular see caustics. So this is the propagator at a fixed time as a function of the initial position and the final position. It's kind of beautiful that this path integral leads to an interference pattern just like what you see in wave optics, where you consider lensing, for example. And to make it more concrete, you see caustics. And caustics are basically organizing the path integral and the propagator neatly. So for example, if you have the potential well, then you can look at the equation of motion, the classical equation of motion, and given an initial position and a final position, you can look for the number of real solutions. So for example, here in the center, you see that there are 7 solutions, classical real solutions to the equation of motion, which leads to a contribution to the path integral. So these are saddle points along which you do have to do these integrals. And this is also what you see here, because here you have a single solution. If you go here in, then you have 3 solutions. Here you find 5 solutions. In the center, indeed, you find 7 solutions. And these blue lines are the caustics, which are separating the regions where you have different number of real solutions. You can also do it for the barrier. And then you find that you either have a single solution or you have 3 real solutions. So let's say that you fix the initial position and you let the final position move. And first you have only a single solution, then you see that 2 solutions emerge, and then you see that they here disappear again, and you are remaining with a single solution which rolls over the barrier. It's kind of nice, and I was surprised that I couldn't really find this in standard textbooks, that if you do tunneling experiments, then there are normally only 3 solutions, not 2 or not 4, but always an odd number, and it's kind of beautiful how the geometry kicks in. If you now take the propagator for this barrier, then indeed you find these caustic regions. So you can see it, for example, here in blue line. And these caustic regions, where you go from 3 solutions to a single solution, indeed order the propagator, which is the path integral we are trying to evaluate. And it's not only in the path integral, in the propagator when you make these plots, but if you actually solve the Schrödinger equation and you bounce a particle off the barrier, you can actually see these 3 solutions. And basically you can see it in the fact that you here have a multi-image region bounded by these caustics. So the green lines are the caustics, which correspond to these blue lines. And they allow you to predict qualitatively what the Schrödinger equation is going to give you. So finally, let's consider complex solutions. So far we only considered real solutions, which is a good starting point for WKB. But of course, we also would like to have complex solutions, as for example done in the no boundary proposal. So let's take the potential well. And here you see the caustic structure. This is basically for 3 different h-bar. So you see that here you are in the quantum regime. Here you approach the semi-classical approximation. The caustics get more pronounced. And what you can do is you can evaluate in blue here the absolute value squared of the propagator. So that's here in blue for this h-bar, here in blue for this h-bar, and here in blue for this h-bar. What you now can first do is you can do a WKB approximation using only the real saddle points. So the WKB approximation is just a saddle point approximation. And what you get is these black curves. So you see that in the 3-image region, or the 3-solution region, the WKB approximation does a reasonable job. So the black line starts to overlap with the blue line. However, for the single image region, it does a terrible job. It drops to infinity at the caustic, which you would expect because WKB breaks down. But afterwards, it drops just to a constant. And this is where you expect the complex solutions to become important and basically quantum tunneling to come in. So what you can do is you can say, well, let me now look for all the complex solutions to my equation of motion. And so what I've done here is I've set the initial position to be -5. And what I've done is I've screened complex initial velocity space. So I've tried all kinds of different complex initial velocities and have checked where does the particle end up if I start with this complex initial velocity. Of course, normally you end at a complex final position, which is completely useless. However, here all the green lines are the lines where the final position is actually real again. So these are potential saddle points you would like to include in your path integral. And what we find is indeed there are complex saddle points which fill this gap. And they run along this green line, so this small green line. So there are also saddle points here and there, which are completely irrelevant to the path integral. If you add them, you get something different from the exact result. But if you dig them along this green line, you find that you indeed get something which starts to resemble the exact propagator. However, then you run into a problem. After you go to a final position of 1.5, this saddle point ceases to exist. So it just disappears. And what happens is that your classical trajectory, which goes into complex plane, hits the singularity of the cosh, so the singularity of your potential. And afterwards, you are in this regime where you have passed this barrier, basically, and you just don't end up at the point you are trying to shoot to. So after 1.5, the WKB approximation in its naive way just fails because the complex saddle point which you need to include no longer exists. So what you can do is you can say, well, let me see this as a branch cut and analytically continue beyond this barrier, which is this pole crossing where you hit the singularity of your potential. And then everything works again. So you see that you have, again, a WKB approximation which does exactly what you want and approximates the real, the exact results very neatly. However, now you have to basically think deeply and philosophize with yourself, because in the region of bigger than 1.5, where you need this analytically continued saddle point, you get a perfectly good result. However, you don't get a solution to your boundary valley problem. So there simply is no classical complex path which allows you to do WKB beyond this barrier. You can still do the path integral, Picard-Lifshitz theory still applies, but you just don't find a solution to your equations of motion, which interpolates between the initial and the final position of your path integral. This is something I only recently discovered and find very curious, but it's kind of neat that by studying such a very simple model, which is of course a lot simpler than quantum gravity, you already can find new phenomena which were, as far as I know, not known. So I've also studied this in the discretized theory, and it looks to be hidden in there. But if you look in detail, you still find the same phenomenon, where if you hit this branch cut, the discretized theory basically gives you false results. So this is, I think, something we should investigate further. Of course, this might be a higher order effect, which only occurs when you have complex saddle points which give you a small contribution. However, since gravity has so many singularities, it might also be, in some circumstances, an important contribution. And by just solving the equation of motion, we just might miss the whole saddle point, which is kind of mind-blowing to me. So just to summarize, interference is a leading property which is very universal in our quantum universe. It's also, of course, in classical physics important. However, the path integral, as we normally see in PET textbooks, is not an integral to mathematical standards. And we should care about that, because if we want to use techniques of integration theory, then it better be an integral. Using Picard-Lifshitz theory, we claim that there exists a path integral which can be defined on the Lifshitz symbols of a certain set of complex saddle points which correspond to instantons. However, it might be a little bit more subtle than you would hope, and there is the question, of course, to find which saddle point is actually relevant and which saddle point is not relevant to your theory. This is actually something, a formula which the resurgence community have started to arrive at via different means. So the derivation is different, but the result seems to be very similar. They basically guessed the same results, which is kind of fascinating. So we only discovered that after we did our research. It seems that instantons go beyond complex classical paths, which I find still astonishing and would like to learn more about. And I hope that these techniques will ultimately be applicable to quantum gravity, where we can try to rigorously define the path integral for gravity and start to evaluate it in different circumstances without having to fudge anything or without having to do questionable steps. So I would like to have it very sec and try to do it step by step, where we can understand all the mathematics, since we don't have a lot of observations. So in many circumstances in physics, we are allowed to make all kinds of leaps because we can subsequently test with experiments whether it works. But I think in quantum gravity especially, it's really important we try to stick very rigidly to the mathematics, because that gives a lot of restrictions to our theory, which is also fun because you can learn things which you didn't set out to learn. So thank you very much for your attention, and happy to take questions.
Okay, thank you, Job. We have some question here. I can give it a mic.
Yeah,
Thanks, Job. I had a question about something you spoke about in the beginning, which
Yes.
is to do with the fact that you have a sigma algebra and the measure should extend to the full sigma algebra. So, just defining any integral. So in the case of, once you have the path integral, of course, now you don't have real measures. You can think of it as a complex measure.
Yes.
And in which case you do have theorems. I mean, you're not guaranteed the complex measures extend, but if they satisfy certain convergence properties, then complex measures can extend. And so have you, in your examples, of course, so where does the whole structure of the sigma algebra come in to these examples? I guess it's much simpler, but even there you have just like a Brownian path, you have the measure, you have the sigma algebra of the set of paths. So where does the complex measure come in? So
Yes. So the first thing to say is that the sigma algebra we take is just the same sigma algebra people take in Brownian motion. So that's the Borel sigma algebra over subsets. So it's like you take all paths which are continuous but not smooth, and you can say, well, I consider my algebra where I make small windows and I want the path to pass through these. So that's the algebra, and then you have the measure, of course. And what we find is that basically this is a complex measure, but it's dominated by the Wiener measure. And that's important, because if it's dominated by the Wiener measure, you can use some very elementary mathematics to show that it inherits all the sigma measure properties. So since it's dominated by this free theory, or the Wiener measure, or however you want to call it, it inherits all the properties you need in order to define integrals. So it's a little bit like the Feynman-Katz formula, but then for real-time processes.
Okay, there is a question there. Could you please?
Sumiti and I are bookending your talk. Can we look at the Pachteller at the very end?
Sure. Where?
The very last slide where you were talking about WKB. Sure, here's fine. So I just want to understand one small piece, and then I have a bigger question. You said that the WKB in the classically forbidden region, that is to the right of the caustic, you said the solution was essentially constant. Did you just mean that it was exponentially suppressed, or did you really mean it was constant?
Well, it's not strictly constant, but it looks like a constant line here.
Okay.
So the black line.
So you just mean it's exponentially suppressed?
Yeah, so WKB for only the real saddle point.
Okay. And then I'm curious about this phenomena you described of hitting the singularity of the potential. And my first reaction was that it would just be a resurgence. That is, that you're just going to continue to a different exponential branch on the other side. But are you saying it's different from that or not?
Well, no, it's exactly that. But if you start with these saddle points being solutions to your shooting problem, your boundary value problem, and now you go across the branch, and you say, oh, well, might that also apply to some boundary value problem? And the answer is no. So you have an instanton, or you have a saddle point, but you have no classical space-time associated to it. So we often talk about these saddle points as being a complex space-time, for example, and you have a Lorentzian region, you have a Euclidean region. But here you have a circumstance where there just is no space-time. There is something you can compute using analytic continuations, just like you described, which is perfectly fine as it seems. But there's just no classical path associated to it.
So, but we understand well what that resurgence is, no? That it's just, we're using exponential forms because they're easy to deal with, right? E to the I times a function is easy to deal with. It's a nice basis, but that couldn't possibly match the analytic structure of the potential, and so you're just going to a regime where you have to use another set of exponentials as your basis, no?
I don't think so, but maybe we should talk
discuss
about this offline with the blackboard.
Yeah.
Maybe I'm just misunderstanding what you're saying.
Any further question about this? Yes. There's one here down.
There is one thing that I didn't quite understand with this Picard-Lefschetz. You introduce a regulator, and then if you can go to that slide back again. So you introduce a regulator, then you write the integral as a sum. Yeah. And then take the limit, and then the regulator drops out.
True.
But the sum is being defined by this, so the domain of integration basically is still being dictated by the regulator, right?
So what we decided to...
So what you are summing over in the end depends on the choice of the regulator.
No, so
right?
we took the saddle points of only f.
Oh, okay. So you
for exactly the reason you described, and of course we choose our regulator to be featureless as possible, so to say, that it doesn't influence the structure in the intermediate steps.
Mm-hmm.
So the point is that if you on the left you are not allowed to put a limit inside.
Right. Yeah,
but then on the right you are, and that's kind of fascinating because you have now a large class of regulators which are not influencing your final result, which is nice.
Mm-hmm. Okay. So the set of saddle points is only defined by f, not by the regulator.
Exactly.
Okay. That's what I wanted to know.
Okay, so thanks you, Job again. Yes, so now we have 10 minutes. If there are further questions for all the three speakers, discussion, complaints, anything, you have all the freedom now. Well, 10 minutes freedom now. Yes, if you want to speak, two speakers come to be here in case, yes. Any other question was left? Yes.
Yes, I start by a question to Sumati. So, I don't know, everyone was citing what Bylog said this morning, so let me do the same. Of course, he questioned, what on earth, why are you so much glued to G mu news? And it seemed to me, from the logic of your presentation, you're also very much glued to G mu news. You somehow seem to treat them extremely seriously because you're requiring, they should be approximating your, Lorentzian object. So that seems to me a very much a classical way of thinking. If you take the more quantum way of thinking, is to say, okay, these whatever discrete structures you have, they are the real thing.
Yeah.
And there is where, I should, for instance, look for interesting signatures, quantum signatures, right? So
Right.
I'm slightly worried by, choosing some measure where, which you, draw out of a hat, that, you are forcing things to look very classical and you may be just missing interesting quantum structures.
Yeah, so I completely agree with you. I think, and I may have misrepresented the point of view here, but this was the other side of the coin. I was trying to look for the, what did he call it? I can't remember, top up or bottom down, whichever. But definitely in the causal set approach, I mean, we're motivated by Lorentzian geometry results, but we just let go of everything, right? I mean, we have no regularity. We have a very, very discrete substructure where we say we include everything in our path integral, including things that are not like continuum. And so as you saw, there were things that, these layered posets, which are very much not like the continuum, but you want to know how they contribute to the path integral. And in some limit, and I agree that in the deep quantum regime, it doesn't have to look anything like space-time. In fact, I think, so the point was not that the dynamics should spit out something that looks like the continuum. Even in the state sum models, you have one phase that looks like the continuum, the other phase does not. It again has a layered structure, which has potentially very interesting physics in that we only know the 2D version of it, so potentially interesting physics is, of course, within quotes. But nevertheless, that's sort of the philosophy. Here the question, I think, and I seem to have missed somehow conveying this, but the point was that once you have your theory, so your theory spits out something, how do you correlate it to, say, de Sitter space-time or something that we know in the large scale? And that's why I'm trying to say that in every theory, whatever your fundamental degrees of freedom are, you will need at some point to be able to make that connection. And then the question will be, what of your fundamental degrees of freedom resemble, space-time in the large? And that will have to be a scale-dependent question. Pretty much like if your theory spat out 4 times 6-dimensional Calabi-Yau compactified space-time, if it did, then you would have to ask, well, okay, at the scales, these compactified things are really small, and so they don't appear in the world as we know. So that's sort of the broad philosophy here, is to say that the continuum approximation that we worry about in causal sets is actually something that's broadly of interest to quantum gravity. But of course, in the deep quantum regime, yes, we have nothing like space-time, and we're happy with that, and we're not trying to get rid of those structures. It's just that we want to also understand how entropy and action play out, and in one case we've seen that entropic contributions are suppressed by the action, but it doesn't mean that we get out continuum spacetimes. So I don't know if I've answered that, or we can continue.
Not fully. I mean, let me get back to the Gemian news, right? So of course, I think it's clear that one has, one needs observables in the quantum theory, and at least for some of them, one wants to show that they have good classical limits. But it seems to me you're asking for much more by, approaching then the space-time, which maybe one could think of as a very well-functioning fiction, which
yeah,
does
I agree.
work.
So it is a fiction. I completely agree that it's a fiction, but you want features of that fiction, just like you want features of a fluid. You want, you want viscosity. You want all of this, but viscosity is a fiction. You really have molecules running around in the substratum, and so these are good, effective degrees of freedom which you would like to recover in your theory. That's all.
Oh, there is another comment. Just throw it.
Hi. Okay. So I have a question for Seth and maybe also for Joe. So at some point you were showing the results of your of the Picard-Lefschetz theory, and you said that you were this method was selecting the Vilenking saddle points, yes. Right?
The what?
The Vilenking.
Yeah, right.
Yeah, and so you said, this is the same result that Job and collaborators obtained.
Right.
So, but as far as I remember, this is problematic because these saddle points lead to unstable perturbations. So I was wondering if you've been thinking about that, and what this like. Does it mean that your calculations are unstable, or?
Okay.
Yeah.
So,
thanks.
Sure. I mean, the part that I talked about was about the causality violations. That was the suppression part on choosing that side. But indeed, I don't know about these unstable perturbations for the Vilenking side. So by choosing, it's just like if you follow the Picard-Lefschetz, it takes you to this side of the path integral. I'm not aware of these. Maybe you have something?
Sure. So we indeed found that these leads to instabilities, and that was a problematic feature which we talked about a lot in several papers with Thomas Hertog and Hartel and Halliwell. So you should keep in mind that it's only one sign which is the difference between the two. So it turns out that you can, if you really want to, you can basically prepare your initial state to get the desired result. But then you have to ask yourself, have you really predicted anything? Because then you have basically forced the sign yourself. So our current understanding is we couldn't find any mistake in the mathematics. So maybe the no boundary proposal is not the Big Bang. So maybe there's another model which needs to be incorporated, or maybe there is a detail in the no boundary proposal which is not currently well enough understood. So that's how we basically think about it. And what is kind of good to mention is that we had a long debate with Hartel and collaborators on this, and in the end they decided to drop the path integral. So they decided, well, let's the BKB approximation be a solution to the Wheeler-DeWitt equation. So that's the way they, at the time, resolved the issue, so to say.
But so the question was more like, is this problem also a problem in the Regge calculation? And
I think you want to urgent comment about this.
Yeah, thank you. Well, this Regge approach eventually will allow us to possibly do this calculation in not in a field theoretic way, but with finite number of variables. And I do think that the problem Job discussed comes from doing it in a way where you first consider the homogeneous integral and then put perturbations on top of that. So if you are able to consider the complete non-perturbative system, then what would happen if the tensor perturbation, or if we want to consider actually anisotropies, are growing, at some point you are forced to the other saddle point. And so this instability will regulate itself in some sense. And that's what we expect to see in the Regge case. Indeed, one can already see that this competition already in the simple system between the cosmological constant term and the conformal factor term, that it depends, on your boundary conditions where you end up with a saddle point. So it's, in my understanding, your result is something like, oh, you shouldn't maybe do perturbation theory in this context, rather than maybe the physics is wrong, but that's my personal interpretation. So
also an option, I agree.
Yeah, he agrees. Any other comments, question? If not, I think we can close here. We would thank again the three speakers for being here. Yeah, have a good afternoon.